You tap the pay button on your phone, $100 to a friend. The screen shows a spinner, then a red banner. Payment failed, please try again. So you tap it again, this time it works, green check mark. But your bank balance just dropped by $200, not one. What happened? The first request actually reached the server. The charge actually went through. The bank actually moved your money. The only thing that failed was the response coming back. A flaky connection, a dropped packet, a timed-out load balancer. Somewhere on the way home, the success message got lost. Your phone never saw it. So your phone did the only sensible thing a phone can do, it retried. And the server, which has no idea this is a retry, did the only sensible thing a server can do, it charged you again. This is the double charge problem. And it shows up everywhere there's money, or important state, or anything you really don't want to do twice. Today we're going to fix it with a tiny pattern called idempotency-keys. So your first instinct might be, just don't retry. If it fails, show an error and stop. Problem solved. Except retries are not your decision. Look at what's between your app and your database. The mobile SDK retries on connection errors. The load balancer replays requests when a backend times out. The reverse proxy has its own retry budget. The message broker redelivers when a consumer crashes mid-processing. Even the kernel's TCP stack retransmits packets you never asked it to. Every single one of these layers was written by a different team, ships with retries on by default, and has no idea what your business logic actually does. The deeper reason is just physics. The network cannot answer the question, did the request arrive? When the response is missing, you literally cannot tell the difference between the server never got it and the server got it but the reply was lost. Silence is ambiguous, and silence is the most common failure mode. So retries aren't optional. They aren't a design choice. They're built into every link in the chain. The job is not to stop them, the job is to make them safe. Before we get to idempotency keys, let's burn through the obvious solutions, because their ghosts haunt every codebase. First fix, check before you write. Look up whether the charge already exists. If yes, skip. If no, insert. Two threads racing the same retry both run the lookup, both see no row, both insert. Two charges. This is a classic time of check, time of use race, and it shows up the moment you have any concurrency at all. Second fix, slap a unique constraint on order ID. This actually works for create order because there's a natural unique key. But what about issue refund, or send email, or submit invoice approval? Most mutating operations don't come with their own unique key. Third fix, just be smart on the client. Detect failure, look at status codes, decide. The problem is the client cannot distinguish a real failure from a successful request whose response was lost. From the client's perspective, both look identical. We need a generic mechanism, one that works for any mutation, doesn't depend on natural unique keys, and doesn't require the client to be psychic. Here's the idea in one sentence. The client generates a unique key per logical operation, and the server promises that the same key always produces the same effect. The mechanics are tiny. Before sending the request, the client makes a fresh random ID, usually a UUID version 4. It attaches that ID to an HTTP header called idempotency-key. Then it sends the request. If the network drops the response and the client retries, same key. Same key on every retry of the same logical operation. That's the contract. On the server side, there's a small lookup table, key to response. When a request arrives, the server checks the table. If it sees the key already, it returns the stored response without rerunning the work. If it doesn't, it runs the request, stores the result against the key, and returns. That's it. The whole pattern is 6 lines of pseudocode. The header carries the key. The cache remembers what happened. Retries become safe because the second, third, and 10th call all hit the cache and replay the same answer the first one produced. The key is the client's promise. This is the same operation as last time. Honor that promise and double charges disappear. Now zoom into the server. A given idempotency key is in one of 3 states. State 1, new. The server has never seen this key. It writes a row, takes a lock, and starts doing the work. State 2, in flight. The server is already running the operation for this key, and a second request shows up with the same key. This usually happens when a client gets impatient and retries before the first one finished. The server responds with a 409 conflict, please wait, request still running. State 3, completed. The work finished, the response is stored. Any future request with this key gets the cached response, no re-execution. The way you actually do this in a database is a single insert with on-conflict do nothing. If the insert succeeds, you're the first one through, do the work. If it doesn't, the row already exists and you go look up what state it's in. The lock is the part that's easy to skip and easy to break. Without it, two retries arriving at the same instant both think they're new. Both run, both charge the customer. Skip the lock and your idempotency key isn't actually idempotent. So the pattern is 3 states, 1 row, and 1 lock. That's the spine of every real implementation. Here's where it gets nasty. What if the server crashes halfway through the operation? Imagine the steps. Write the order row, call Stripe to charge the card, send a confirmation email, write the response to the idempotency key. 4 phases. Now the server crashes right after Stripe charged the customer. The card is debited. But the response was never stored, the email was never sent, the row says in flight. The client retries with the same key. A naive implementation runs the whole operation from the top. Stripe gets called again. The customer gets charged a second time. The fix is something called recovery points. The idempotency key row gets an extra column that ratchets forward as you complete each phase. Started, order created, charge created, email sent, finished. Each phase between 2 foreign side effects is wrapped in a database transaction. The recovery point is updated atomically with the work. So if you crash, the recovery point tells the next request exactly where to resume. On retry, the server reads the recovery point, sees charge created, and skips the charging step entirely. It picks up at send email and continues. The customer gets charged once. The email goes out. The response gets stored. The retry was safe. This is the bit that real implementations get right and toy implementations get wrong. There's one more piece. Your server probably isn't the end of the chain. When a payment app charges a card, the request goes phone, then your API, then Stripe. 3 hops. Each hop can drop a response. Each hop has its own retries, so idempotency at your layer alone is not enough. The trick is to chain the keys downstream. Your API receives an idempotency key from the phone. When it calls Stripe, it derives a new deterministic key from that one, say, a hash of the original key plus the string Stripe charge. That derived key rides along on the call to Stripe, in Stripe's own idempotency-key header. Now imagine the connection between your API and Stripe drops. Your API retries. It computes the same derived key because the inputs are the same. Stripe sees a key it's seen before, returns its cached charge response, and does not charge the card again. Idempotency composes. As long as every layer derives a stable key from the upstream one, the entire chain becomes retry safe, even when individual hops fail in different ways. This is what production payment systems actually do. The key from the phone is the seed. Every downstream call gets a deterministic derivative. The whole pipeline becomes a single, retry-safe operation from the user's tap to the final ledger entry. 4 edge cases that bite real implementations. First, time to live. You can't keep idempotency rows forever. Stripe stores them for about 24 hours, then prunes. The reason is simple: the table would grow without bound. But there's a consequence. If a client retries after the key expires, the server treats it as a new request. So pick a TTL longer than your client's retry budget. Second, body mismatch. What if a client sends the same key, but with different parameters? Same key, but the amount changed from 100 to 200. The server should refuse. The key is a promise that this is the same operation. A different body breaks that promise. Stripe returns a specific error in this case, rather than silently returning the original response. Third, scoping. The key alone is not enough. Two different users could happen to generate the same UUID, or one user could try to attack another by guessing keys. Real implementations scope the key by user ID or API key. The actual lookup is on the pair, not just the key. Fourth and most important, the key must be generated by the client before sending. If the server generates the key, the client has no way to recognize a retry. The whole point is that the client tags the operation up front, so any future retry of that operation can be correlated. Get any of these wrong, and your idempotency layer leaks. This pattern is everywhere. You've probably already used it without naming it. Stripe is the most famous one. Every mutating endpoint accepts an idempotency-key header, 24-hour cache. The blog posts that define the modern style of this pattern came from Stripe's engineering team. Oz uses the same idea under a different name. The parameter is called client request token or client token, and you'll see it in EC2 run instances, CloudFormation create stack, and secrets manager put secret value. Same pattern, slightly different vocabulary. Square calls theirs idempotency key in the JSON body rather than a header. PayPal, Adyen, and Shopify each have their own variants on every payment endpoint. Even your database does this. Postgres insert on conflict do nothing is the idempotency key pattern at the storage layer. The unique key is the operation key, and the conflict resolution is the cache hit. Kafka's exactly once semantics work the same way. Each producer gets a producer ID, and each message gets a sequence number. The broker dedupes by that pair. It's an idempotency key in disguise. Anywhere money is mutated, anywhere state is created, anywhere a retry could be expensive, somebody has put this pattern in the way. Once you know the shape, you start seeing it everywhere. Let's compress everything into a single mental model. Every mutating endpoint will be retried. Not might be, will be. By the SDK, by the load balancer, by the user tapping again. Design for it from the start. The whole pattern is 5 small habits. The client generates a UUID for each logical operation. The server keys responses by it and locks during in-flight requests. Multi-step work uses recovery points so a mid-execution crash resumes correctly. The key is passed downstream so dependencies stay safe too, and the time to live is longer than your retry budget. Get those right, and something quietly amazing happens. The same charge request fired 5 times in a row produces exactly 1 charge. 4 of the requests bounce harmlessly off the cache. The user gets charged once, no matter how many times the network screams. The network drops messages. That's its nature. Idempotency keys are the trick that turns those drops from a correctness problem into a non-event. Build them into every mutating endpoint. Pair them with retries and exponential backoff. And the next time someone asks why their startup's payment system never double charges anyone, you'll know exactly what's holding the line.